Thank you, everyone. As Oliver mentioned, I'm Chris Mattia, and when I got my ham radio license, I took some classes, and I worked through a lot of the materials myself, and I thought I've got 25 years of higher education experience teaching faculty to teach with technology, and I thought, wow, there really needs to be some better instructional content on ham radio and emergency communications. And so I set up Wave Talkers, and as part of setting that up, I've reached out to many different vendors. So a lot of the products that you see are ones that have been sent to me by companies such as Bioenno Power, Power Film Solar, Buddy Pole, and several others. But I'm not necessarily endorsing any one product. What we're going to talk about is how you operate and how you work with some of these things. So what I'm actually going to be talking about is back in 2019 at the Baker to Vegas race, I operated as part of the medical radio network, and I was responsible for stages 6, 7, and 8 medic stations that were there. And when we got to stage 7 at the 2019 B2V race, what we had to do is we had to set up the what we call the MRK, or the medical radio kit radio for the station. We had to get the medic on the air, and we had a network that was connecting all the way back to Central Dispatch back in Las Vegas. We had a couple of medic bases that we had to connect to, and we had to keep that station on the air the entire time. So these were the radios, and I had no previous experience with these prior to getting out there for the race. They're a commercial radio. It's a Harris radio. On the side of the radio, you can see. Let me see if I can get my mouse over to the right screen. Hello. Whoops. Back. It's always better when you can get your mouse to drive where you want it, and it's not driving. Okay, so on the left-hand side, you can see there's a mag mount antenna, and that mag mount would just go up on top of the medic's car. The medic would pull their vehicle up. They would then, where the speaker is down at the bottom, you see there's a little coil of wire. That was the external speaker that was there, but that coil of wire has a 12-volt aux plug, and we were going to just plug right into the cigarette lighter adapter of the medic's vehicle. But when we got to stage 7, we discovered that medic didn't have an aux plug that was functional in their vehicle. So we needed a way to be able to get this radio on the air right away and keep it on the air for the entire time. So as an emergency communicator, and this is what we're going to be talking about, we're going to explore the concepts of how you do this throughout this talk. So the first thing that we do as an emergency communicator is assess the situation. You want to identify the challenges and the problems. You want to prioritize your solutions, and you want to come up with some resolutions to those. So the first thing that we need to do is we had an immediate need for emergency power to get this MRK up and on the air. The second need that we had was to sustain that power to operate that station for at least 15 hours. That was, at that particular stage, the length of time that we were expecting to need that medic station to be on the air. Obviously, having it on longer would be better, but this was the basic parameters that we had to work with. And you can see here's that 12-volt auxiliary plug. It's just coiled up down here at the bottom. So in the absence of having the vehicle for the medic as it was originally planned to be able to plug into, we had to come up with some ways to get the station on the air. Now, the first option would have been obviously to just pull another vehicle up, park it in that location, and plug the 12-volt auxiliary plug in there. At the time we were getting set up in the morning, though, we did not have another vehicle that was available that we'd be able to leave there all day long. So this ended up not being an option for us for this particular situation. So then we thought, okay, what else could we do? Well, we could get a generator, and with an AC inverter in it, we could plug in some 12-volt power and get that all set up. It's a great plan. You can keep the thing up and running for a long time, but you really need to have a generator and fuel in order to implement that plan. And I didn't have one, and we didn't have one available to us, since I need to get this station up on the air. The next was to use a battery. Now, this could have been any type of battery. And if you see in the picture in the background, there are some other batteries stacked up in there. And I was working on radioing back with some requests back to our base to say, hey, can you send us down a battery? But we needed to get the medic on the air right now. So I needed to use the equipment that I had on hand to get them up and running. So when you think about a battery choice for MCOM, and throughout this entire talk, the focus is entirely on emergency communications, the power use that you have with emergency communications specifically. So I'm going to break the world of batteries into two very broad categories. I'm going to say traditional batteries over here, and I'm going to say modern batteries over there. And when I talk about traditional batteries, what I'm referring to are your typical lead acid or flooded batteries. You can see here, there's the battery out of my Mini Cooper. It's a traditional lead acid battery. Other types of traditional batteries, as I'm defining them for the purposes of this talk, would be AGM or absorbed glass mat batteries. These are a fairly new technology, and also gel cell batteries. Now, one thing to note here is that on your traditional batteries, that's your lead acid batteries, we usually think of lead acid batteries as the starter battery in your vehicle, and these gel cell and AGMs as more deep cycle batteries. Of course, there are variations of these that are out there, but that's the kind of the general framework that we're talking about here. When we think about modern batteries, there are lots of them out there, but I'm really only going to think about two types of modern batteries: the lithium ion batteries and the lithium iron phosphate batteries. And we're going to just talk just a little bit about, and there's of course lots of other more modern chemistries that are available in batteries, but this is the world that we're going to focus on for the purposes of emergency communications in this talk. So let's talk about traditional batteries just a little bit. We'll talk about the advantages and the disadvantages of these batteries. And first of all, on the advantages side, these generally have a very high capacity. They can store a lot of energy inside of these traditional types of batteries, which is great because you want to get on the air and you want to be able to operate for an extended period of time. So your traditional batteries certainly can do that. They are relatively inexpensive. A lead acid battery or some of the AGMs and the gels are a little more expensive, but you can generally pick these up pretty cheaply, and you can get them pretty much everywhere. I mean, you can get them at the big box stores, you can get them at auto parts stores, marine supply stores. There, you can get them online. You're gonna pay more for shipping. We'll talk about that in the disadvantages, but they're pretty much, you can get them anywhere. There are deep cycle models available. Now let's very briefly talk about deep cycle versus starter batteries. So in your vehicle, you have a starter battery that starts your car. And the purpose of that battery is to deliver a lot of power really fast to your starter so it can start the engine, and then your alternator kind of takes over and can throw some energy back in. So in order to do that, inside of the battery itself, there are these oftentimes lead plates that are in there, and they're very thin because they have a very high surface area to volume ratio in order to deliver a lot of charge and a lot of power to start that battery. When you talk about deep cycle batteries work under the same basic principle, except for the plates that they're using are much thicker, they're much heavier, and they allow the battery to be discharged and not be damaged. Every one of us has been in the situation where we've had the battery in our vehicle, probably over the past year, where we haven't been driving our vehicle and it's sat there for a long time. We've drained the power out of it completely, and we've had to recharge the battery before it will start our vehicle. Once that happens with your starter battery, you seriously degrade the life of the battery, and it never is quite the same again with deep cycle batteries. So I lived on a boat for a long time, so I lived on 12 volts, And you could always, the deep cycle batteries on a boat are really designed for these deep discharges. And as a ham radio operator, you want as much power out of that battery as you can possibly get to keep your station on the air for a long period of time. Okay, so let's talk about the disadvantages. These things are extremely heavy. I like to call them lead mines. And that, for me, takes many of these batteries out of the realm of using them for emergency communications, because oftentimes you've probably seen this. Somebody rolls into to a field day exercise or rolls into an exercise setup, and they've got their lead acid batteries set up, or their whatever gel cells, and they're using a hand truck to roll them in. Well, let's say there's a big major earthquake in the area. How are you going to transport that battery from your location to the hospital where you're going to operate on? It's not going to be pretty to be able to do that. More than likely here in LA, we're not going to be able to drive from wherever you're at into the location. You're probably going to have to do it on foot, and hoofing one of these batteries is not going to be pleasant. So that, just the overall weight of them kind of makes them not as attractive. And the other part of a disadvantage of these batteries is the discharge curve. And I'm going to talk about that in more detail in just a few minutes. But that's kind of the high level of advantages and disadvantages of these. So let's talk about modern batteries. And remember, there's two types that we're talking about. The first is the lithium ion battery. Now, most all new HTs that you're going to get are going to come with a battery integrated into it, and that battery is going to be a lithium ion battery. Of course, there are other technologies that are available. There are a few other batteries that are on the market. Older HTs might have like nickel cadmium or nickel metal hydride or something like that, but most new ones have lithium ions. We're not talking about HTs as in this talk. We're talking more about the lithium iron phosphate. You'll also hear these referred to as LiFePO4, which, if you remember back to your high school chemistry class, which might be a little while ago for some of us, that would be Li for lithium, Fe for iron, and PO4 for phosphate. And so that chemistry, that mix that's in there with that iron, changes the dynamics of how the lithium iron phosphate battery works compared to other lithium ion batteries. You'll also hear these referred to as LFP. So if you hear me use any of those terms, LFP, LiFePO4, or lithium iron phosphate, I'm talking about all the same things. And there's lots of manufacturers that produce these, but this is the one that we're going to mostly talk about today. Now, let's talk about modern battery advantages and disadvantages. First, they have an extremely high energy density, meaning you store a lot of power inside a little tiny package. And that makes for a very lightweight and compact size of the battery. For example, a 30 amp hour lead acid battery is typically going to weigh somewhere in the neighborhood of 20 to 25 pounds. I did some averaging of them. It's about 22 pounds for the most part. The 30 amp hour lithium iron phosphate battery, which is one of these guys here, also 30 amp hours, this is 7.5 pounds. That is a fraction of the amount of weight, meaning I can carry this much further than I can carry one of those lead acid batteries. The next thing is that they have a very high number of charge cycles for the useful life of the battery. Many lead acid batteries and the traditional batteries will degrade over time throughout the different charge cycles that you're using them for. And so you do not get as much life out of the battery as you do, where these lithium iron phosphate batteries are typically good. Most of the manufacturers all claim about 2,000 charge cycles as being available. Now, I've been operating exclusively on my Bioenno batteries for about 2.5 years now, and I've had absolutely no degradation of them whatsoever. I'm really happy with them. I've been using, that's all I operate on. I don't operate off of commercial power ever. I only use batteries. The next advantage is that they have a nearly flat discharge curve. There's that discharge curve thing again. Again, we're going to come back to that in just a second so we can compare them. But these lithium iron phosphates, these modern batteries, have an almost flat discharge curve, and that is a huge deal for emergency communication. Next is the connectors are more suitable for MCOM. Now, what the heck am I talking about there? On your lithium iron phosphate batteries, most all of them are pre-wired with power poles. So you can take these things and you can just plug them directly into your ham radio gear and you're good to go with that. Disadvantage wise, it's cost, like high initial cost on these batteries. And when you take into account the number of charge cycles, the weight and so forth, that really does tend to make it so that the lifetime cost of the batteries ends up being a lot cheaper than a lead acid battery or a traditional battery. But that initial cost is really hard to swallow for a lot of us because that does come right out of our pocket. So let's talk about the discharge curves. So on a typical lead acid battery or your traditional batteries, these are what I have on my boat. You have this nearly, actually I got to go this way with it, I guess. No, I got to go this. This is hard to do when you're looking at yourself backwards all the time in the thing. So the discharge curve is nearly linear on a lead acid battery. So it starts at some level of charge, and then as you use it along the x-axis here, as you start discharging the battery, your voltage drops with a near linear relationship. And so you see that like nice fall off. Now, on living on a boat, I could tell when it was time for me to plug my charger back in and recharge the house batteries because my incandescent cabin lights would start to slowly dim. And I would say, oh, my batteries are kind of low. Let me go ahead and charge the house batteries back up. And then they get brighter again as soon as you turn that charger in. And that works really good. That lithium that you see there, the other curve, the red curve, that's showing you that flat discharge curve. It goes right along the top, and then as the battery is just about fully discharged, boom, it drops off very precipitously right there at the end. So why does this matter, though, for emergency communications? Well, it matters because our radios require a certain amount of power. Now, some radios, they shut off at 12 volts. Many of them shut off at 11.5 volts. They're all different. So for the purposes of simplicity right now, let's assume 12 volts is the cutoff point. So once these two curves fall below that 12 volt line or the 11.5, whatever it is for your particular radio, you're done operating. You're completely finished. Your radio will no longer operate on less voltage. So if we're talking about the lead acid battery, you're looking at somewhere between 45 and maybe 65-ish% of the battery power, that energy that's stored in that lead acid battery, that is usable power for you. That is not a very good deal, especially when you take into account the weight of these batteries. That means you're carrying around a lot of extra lead that you're not going to be able to use the energy that's stored inside of that battery for running your ham radio station. Now, on comparison to that, the lithium batteries that have this flat discharge curve, you're getting somewhere in the neighborhood of 95% of the energy stored in that battery back out as usable energy. When your radio stops working, the battery's mostly depleted at that point. So that's a huge deal. So if we're talking about a 30 amp hour battery, you're talking about getting out like 28 amp hours out of that battery versus a traditional battery where you might be getting only about 15 amp hours out of that battery that's usable. And that's huge for us. So when we think about battery choices, my suggestion would be to go with some type of...
Chris, I think we just lost your sound. No, we can't hear you. Are others able to hear Chris? Shake your head. No?
No,
Okay.
I think that's an internet out or something. Oh, there we are.
I'm back. Am I back?
You're
Now
back.
you're back.
Okay. I'm getting an unstable internet connection here. I apologize for that. At what point did the fluff get in my ear and I stopped speaking?
Why don't you start at the beginning of this slide?
Oh, okay, sure. So, therefore, for MCOM use, I would strongly suggest you choosing a lithium iron phosphate battery to go in your go box, to go in whatever you're going to be taking with you out into the field for all of those different choices that we just talked about. This is the inside of my go box. It's just a plastic ammo can. You can see I've got my D74 or my Kenwood D710G in here. I've got the BioEnno lithium iron phosphate battery, and then the wiring to get all of that power and connections out to the outside of the box. So in one small self-contained unit, this is actually a 30 amp hour battery, and I can run this radio for like forever on this one battery. And we'll talk about how you calculate that in just a second. So the next challenge is, how do you make the connection between the battery and the radio that you're operating on? Now, remember I said on this particular radio, these have the 12-volt plug connections, the aux plugs that typically we would call them the cigarette lighter adapter in your car. And on these lithium iron phosphate batteries, many of them have power poles. So that brings us to the need for having power adapters in your MCOM kit. And I like to go on the philosophy of just flat out power pole everything. Everything you've got that runs on DC power, convert it over to power poles. Now, this is my part of the adapters that I carry with me pretty much all the time. I've got a second ammo can that is just full of a backup battery and then a lot of these adapters. So if you look up at the top, you've got these large alligator clips that connect onto a power pole connectors. Now, these are great because if you go up to another type of battery, or you're out in the field, or you need to adapt to a vehicle, you can clip right onto the battery, and now you've got power out to run your radio gear via power poles. In the middle, you've got ring terminals to power pole connectors. Now, those are really helpful because anytime you've got terminal posts, you can connect those onto some other type of battery or to a device, such as this one right here. This is a power inverter. So I've got 12 volts up at the top that go in on those terminal posts, and I just connect the ring terminals to that. And then down here at the bottom is a 120 volt plug. So I can use this to power my laptop, say for instance, or use it to power some other device if I'm in the field to do that. Up there, I've also got power poles to bare wires. And this is great because when you're in the field, you can't always plan for everything that you may need. So I've got a couple of wires that are set up where I've already got the power poles on one side and then bare wires on the other. So I can quickly adapt to whatever I need in the field if need be. In this next row, this is a connector to some of my solar panels that goes to power poles. Then I've got a Y adapter, so power pole on one side, and then I just connect the positive terminals together, the negative terminals together, and then do two more power poles. It's not fused, and it's not something you would want to use long term, but it's a great way if you need to quickly power two devices off of one source. You can plug one of these little just wires in, it'll just split the voltage between them. Next, I've got some 12 volt plug and 12 volt socket connectors. Those both go to power poles as well. Now you can pick those things up on Amazon for about $3 as a kit. They get both of those in one package, and then just pull the wires out that they come with and solder on your own new wires, plug on some power poles, and now you can adapt. You can plug into, say, a 12 volt socket in a vehicle and get power out of that to your radio, or you have a 12 volt socket now coming off of your battery. You can plug in and adapt any 12 volt plug device that needs that. Now you've got the adapter to do that. For your radios, the next one over there, that's the connection for my ICOM 7300. And all I do is clip the leads off. So I've got the right plug to go into the radio, put power poles on it, and now I can adapt my radio to whatever I need. Now, you always want to put fuses on, so I make a couple of these that are power pole with inline fuses ready to go. So many of our radios come already with that arrangement. I always clip those off, so I've got just the fuses in there, and then I make these little tiny pigtails. So it just allows for more flexibility. Upper right, I've got an extension cord. Now, this is one that I use if I need to run my solar panels out from a further location and pull that power in or connect a device that's further out. It also automatically gives you a length of wire if you need to cut up while you're in the field to make a quick adapter, you've got that spare wire. So it's ready to go as one long extension cord, but then you can chop it down small if you need it. I've got a 12-volt plug connector. That's a USB adapter. You definitely want to have one of these with whatever cabling that you need for your mobile device, cell phone, what have you. Now you can charge your, keep your station on the air with a mobile device if you need to. Power distribution, there's a rig runner over there. These are each one of those power pole connections are fused, which are really nice to be able to use because you can plug one connection from your battery into one end of the rig runner, and then you can power multiple devices off of that. Make sure if you're doing that, though, you're keeping track of the total amount of power draw that all of your devices are using. We'll talk about that more in just a few seconds. I also have a power pole to little small alligator clips used for adapting to small devices. And then down here at the bottom, I guess it's over and pointing in that way, I've got some DC barrel and a DC barrel socket connection. And those are, again, useful for just adapting to lots of things. So whatever the devices are that you use in the field, make sure you can connect those devices to power poles. As an emergency communicator, the ARES standard, the one that all of us use for the most part, are power poles. Now, every one of these things up here, you can buy the cable pre-made. And if you're very rich, you can afford to be able to do that. If you are, give me a call. I can, help you spend some of that money, maybe. I don't know. But for me, I don't have that kind of cash. So what I did is I invested in one of these crimpers and I just make my own cables. Like I get a new device and first thing I do is go in and clip the leads off of that sucker and crimp on some power poles. If you need help learning how to do this, give me a shout. There's lots of videos on YouTube to help walk you through using power poles. There's lots of folks here in the group that can help you with making power poles. It's pretty easy once you figure it out how to be able to do it. And you can literally power pole everything. One of the little projects I've been working on, I've got a mast with a little that I can rotate by hand, but I built this little tiny, let me bring myself back up here. I built this little tiny rotator here. This is just a servo. I did a little surgery on it. It's got a little radio attached and look, power pole connections on that. So I can plug this into my mast and I've got remote rotation of my mast to be able to dial wherever I need. You can literally power pole anything. It's a really good connection. Even for your like link dipoles, they work really well. And if you standardize on one thing, you're really good at making that one type of connection and just adapt it to whatever you need there. Okay, so that's enough about that. So we got our medic station on the air. I've got the battery there, was able to have my spare battery. I plugged in the adaption in it, got the MRK up and running. The medic was able to check in right away. And yeah, this whole process that we just talked about took about 5 minutes to go. We just went in and assessed the situation. Look, we don't have power. What do we have available to us? Well, we got to make sure we can get the power up here. Grabbed the spare battery, walked up, plugged it in, made the adaption. Boom, medic's on the air, ready to go. Now, the next challenge and the next question is really, how long will it run? How long can you keep that station on the air with a battery that's, say, a 30 amp hour battery? That's the one that I had with me because that's the one that I'd sized for my station. And in order to answer that question, I strongly encourage you to think in terms of amp hours. Now, amp hours is one of the measures. There's a lot of different ratings that are on a lot of our batteries. And oftentimes with amateur radio, we're thinking a lot in terms of watts because we've got a 5-watt HT, we've got a 50-watt mobile station, we've got a 100-watt HF station. And a different way to think about that, and in my opinion, a better way to think about that is to simply calculate the number of amp hours, because it's a really simple calculation. Each of our devices draws a certain amount of amps or a certain amount of current that's coming out of the battery in order to drive that device. Our batteries have a rating on them that says how many amp hours are stored in here. Now, what does that mean? Well, an amp hour, let's say we've got a 30 amp hour battery, and our radio or all of our equipment, anytime you see me say radio, I really mean all of your equipment. So if you're running laptops, your laptop is included in that. The radio draws 1 amp of current, let's say. So how long can you run that battery for? Well, 30 amp hours divided by 1 amp would mean you could run that radio for about 30 hours. That would be pretty good. That's over a day. That's really nice. So let's do another one of these. So we've still got our 30 amp hour battery, and now our radio draws 2 amps. So 30 divided by 2, how long can we run that battery for? We can run that radio for about 15 hours. Okay, let's do one more. 30 amp hour battery. The radio draws 10 amps. Suddenly that 30 amp hour battery now can only maintain that radio for 3 hours. That is a huge difference. And that requires just a little bit of calculation on your part to figure out and properly size your system. So when you're going in to buy a battery, you want to take this into account. Now, how do you do this? Well, there's 2 primary ways. The first is to check the manual for your radio. So I have a Kenwood D710G, and I flipped through my manual online and I found this information here. So there is the current drain or the power usage, and you need to take into account both transmit power and current drain during receive. For the Kenwood D710, you can see that current drain on receive says less than 1.2 amps. And that what you really want to do is, even though it says less than, take that as it's going to draw 1.2 amps. You never want to try and guess on the low side. You want to take what's the big amount of battery power so you can really get a more realistic feel. On the transmit side, notice the field changes quite a bit. The radio that I have has the ability to transmit in low, medium, and high power, and both on VHF and UHF, and the power draw on transmit is quite different. For VHF, low power starts at about 4 amps, and on high power on VHF, it's drawing 13 amps. VHF starts at 5, and it goes up to 13 amps. So when you're budgeting your power requirements, you really want to always guess on the higher ranges. Now, that obviously brings up the immediate thought of, hey, if you do not need high power, you can transmit for longer on low power. It's just a straight up way that you can extend the life of your battery. Another thing that you may want to consider here is the use of a Qrp radio. Many of the Qrp radios, such as the ICOM 705, the L-Craft KX3, the Yaesu 818, their current draw 6 milliwatts of power on receive. And so if you think about it, as amateur radio operators, as communicators, we are listening far more than we are transmitting. So if you have a radio that has a much lower current draw on receive, you can operate for much longer. And so that is just definitely something to keep in the back of your mind. But this information is in every one of your manuals. You can go and you can find that information for your particular radio. Now, keep in mind, we're going to look at, we're going to do a calculation in just a second, and we're going to use my Kenwood D710 as the sample, and 1.2 amps on receive and 13 amps on transmit. So we'll come back to that. Now, I mentioned there's 2 ways to be able to do this. Another way to do this is to use a power meter, and that's plugged in line between your battery or your power source and your load. On the left-hand side of this, these you can find them online. They're pretty cheap. This one's by PowerWorks, which is a pretty good brand as far as I'm concerned. It's the one that I use all the time. You plug the source on the left-hand side, that would go into your battery. And then on the right-hand side, you plug your load, the radio, whatever else, maybe your rig runner, and then everything downstream of that. And what this does is in the upper left corner, it measures the instantaneous current draw that is going on right now. So you just plug this guy in, you look at it, and you have your radio, everything's turned on, and you just look and see how much power is my radio actually drawing? How much power is my whole system drawing over time? If you look down the next line down, that tells you that is a cumulative use of power that's flowing through this meter while it's online. And so this is saying that, okay, 5.206 amp hours. That is over time how much power is being pulled out of the battery. There's other values in there like the voltage and the watts that are being used or whatever, but that simple value of amps for what is currently drawing and then amp hours as the length of time that you're able to operate in terms of hours is right there for you. So these are really helpful. And you can also, by the way, because this is source and load, you're able to plug these into any source and any load. So when you're going to charge your battery, you can plug the source into your charger and then plug your battery into the load, and you will see how much power goes into, actually, I would go this way. I would go that way. There we go that way. How much power goes into your battery. So it's kind of like the fuel gauge on your car while you're driving. How much gasoline do you have in there? How many amp hours go into your battery? How much you can pull out of it? Okay, so let's talk about the simplified duty cycle calculator. That's a lot of math to try and figure out. And I don't know about you, but I don't like doing math all the time. So I've got these computers. We all have computers and they do math pretty well for us. So let me drop out of the presentation here for just a second. Let me make sure I got the right keyboard selected. I'm going to grab my slide deck here and I'm going to jump over to this handy dandy little Google Doc, that Google sheet that I created here. And I call this my simplified duty cycle calculator. And what you do is you just plug in the numbers in this yellow box here. The top one is how many amp hours does your battery have? Well, in my case, I got a 30 amp hour battery. I plug in 30. And then how much amps are drawn on receive? Well, right now I've got it set to 1, but on my Kenwood D710G, it is 1.2. Did I get that right? Yeah, there we go. 1.2 amps. And I'll click down in the box below. And on transmit, we said it draws 13 amps. So I'll go ahead and type that in here. 1.3 and enter. And at the bottom down here, what it's telling us is that we've got the duty cycle here. And at 100% duty cycle, meaning we're transmitting all the time, projected listening time is going to be 0 because we're transmitting all the time. He would never do that. Projected hours of transmitting would be about 2.3 hours, and that adds together to a projected total hours of operating of roughly about 2.3. And that goes all the way down to 1% duty cycle, meaning you're listening 99% of the time and you're transmitting only 1% of the time, and you would get roughly about 24.8 hours of operating time out of that. For the most part, unless you're operating as net control, you're going to be operating somewhere in this neighborhood, somewhere in the 25 to maybe even 5% time that you're going to be able to operate. And so for me, for my Kenwood D710G and my 30 amp hour battery, that means I can generally operate for roughly about 20 hours on that particular rig running at high power. And so for an individual emergency communicator, being able to operate for about 20 hours on the air is perfect, because if you can recharge a little bit in between, that means you can pretty much stay on the air indefinitely at that time. Now, let's go back to Baker to Vegas and the situation that we have. And I've got a little cheat sheet down here. I had to do a little looking here to find out how much those MRK radios actually draw. And it turns out they draw 4 amps on receive and 20 amps on transmit. So let's go up here and let's plug those numbers in to find out how we did. 4 amps on receive and 20 amps on transmit. And down in this area right here, you can see that the handy dandy simplified duty cycle calculator tells us we could run that battery for about 7-ish hours. And remember, in the very first part of the presentation, we said our requirement was we had to keep this station on the air for at least 15 hours, which means we're not going to make it. We cannot keep that battery operating for that amount of time. Now, Tran's going to give you a link to this simplified duty cycle calculator. I may have to add you in so that you can be able to access that in just a second, but I'm going to go back over to the presentation now.
Yeah, so yes, it's asking us to request access to that Google Doc that you sent.
Yeah, and I'll put that. Oops, that's not the right one. That's the Solar Power 2. This is the one I want. I'll allow people into it afterwards when we're back going. So here we are, and I'm on the right keyboard, and here we go. So there we are. We're at about 7 hours of operating on this 30 amp hour battery with this particular radio for the particular setup. And that's only about a 10% duty cycle. So that's not going to cut it. What are our options? We can reduce transmit power if possible. That will certainly gain a little bit more life out of the battery. However, remember, this is the medic station, and let's say an emergency comes up and we need to connect 120 miles across the desert with these suckers. And we were finding that lower power was just not cutting it. We really needed to be on high power to make those kind of leaps to be able to communicate with all of the right places. So reducing power, turns out for this situation, was not an option for us. We could use some backup batteries, and that was a great thing. We got the station on the air. I could call back to base and say, hey, I need some more batteries to be able to do, and we could just swap in batteries. That is certainly an option. You got to carry more weight with you, or you can augment the battery power. And this is clearly, what we were going to do. We're going to plug in solar and back up the battery. So we're constantly charging and putting some of that power back into the battery as it's being drained out while it's in use. And that is the solution that we ended up going with. So let's talk about MCOM power generation, which is used for keeping your station on the air. Now, in an ideal world, we would all, as emergency communicators in our go bag, would be able to carry about 2 to 3 days worth of MCOM power to keep our own personal station on the air. However, that's just not feasible for most of us to carry that much power. Now, if you're running a QRP rig, yeah, maybe a 30 amp hour battery could run an ICOM 705 pretty much until the heat death of the universe, with just how much that the radio just sips power out of it. So a 30 amp hour battery for that radio would work great. However, in this situation, it's not going to work for us. It's just not going to be feasible. What you really need to do is generate enough power to augment that MCOM to meet your power goal. You don't always have to carry all the power with you. You can bring a little generator with you to do that. Now, the primary options for this: fossil fuel generator, big, stinky. Again, if you're being deployed, let's say you need to, you get called up to head for a major earthquake, you're probably not going to carry your gas-powered generator with you and lug it across the city. You're probably not going to be able to set up a wind turbine because of the blades spinning around and making sure it's safe. It's probably not going to work pretty well. Certainly in LA, hydropower is not going to be an option for us. So that means solar panels. We've got a lot of sunshine here in Southern California. That's going to work just fine for us. So that's what we're going to talk about mostly. And we start thinking about solar panels. There's 3 basic types of panel technology out there. The first is a monocrystalline solar panel, and I've got one of those. I've got one of those right here. This is one of the portable BioEnno panels. The monocrystalline panels, oftentimes they appear black. Not all of them, but for the most part, the panels themselves appear black. They oftentimes on the rigid panels will have this diamond pattern as the interconnect. Again, not always, but it's one of those like leading indicators. Now, what do I mean by monocrystalline? Now, each one of these little squares here, the black squares, that is an individual wafer of silicon. And that crystal is grown from one single crystal, and then they're laid out in an array and they're connected all together. They're wired up either in some combination of series or parallel. We'll talk about that more in just a second. These monocrystalline panels are generally the most efficient that are currently commercially available. They also come at a pretty high price. They're a little bit more expensive, but they deliver a lot more power out of the crystals. And that's the monocrystalline one. The next one would be the polycrystalline, meaning many crystals. And the way that these are formed, each of one of those squares are usually laid out in a hash pattern of multiple crystals, and then they're sandwiched and glued together. They work pretty good, but they're a lot less efficient. So if you go to one of the big box stores, you go to like one of the cheap discount places, and you get the really good deal on your solar panels, more than likely they're going to be polycrystalline. monocrystalline panels, which means they're not going to be as efficient. They're a lot cheaper to grow because you don't have to grow as big of a quality large crystal to do that. You can usually identify these because they've got this kind of shimmery look to them. They're oftentimes very blue in color. Again, not always, but they have this kind of shimmer. And if you look closely at the crystals themselves, you can see that it's this mismatch of little crystals that stack onto each other and that are all laminated together. For MCOM use, I would not suggest polycrystalline panels because they're going to be bigger. They're less efficient than their monocrystalline counterparts, which means they're physically larger. And if you've got to transport them, they're just bigger to be able to do. You need to carry the power with you that you've got. That brings us to a third type, and that would be thin film panels. Now, the thin film panels use a variety of different technologies out there, and they are flexible. So for instance, this is the power film solar panel, and you can see the panel itself. This is a 60-watt panel. They're completely flexible. You can do all kinds, you can bend them around, you can lay them out flat, and they fold up really small. They're easy to carry. This here is a 60-watt panel. We'll show it more in slides. This is a little small, hard to show here in the booth. But they're a lot more expensive. They're not as efficient as the monocrystalline panels. So you need a bigger array of these cells in order to generate the same amount of power. So for size-wise, your monocrystallines are going to generally be the most efficient at generating the most amount of power for their size. Next would be polycrystalline, then would be the thin film. But the thin film, in my opinion, kind of wins out because you can take one of those things and you can pop it in your backpack, and they're really light and you're able to carry them. However, they are by far the most expensive panels that you're going to find commercially available for MCOM use today. So that's the three types of panels that we're talking about. Now here's I promised we'd show you a picture of the boat. Here's my boat that I lived on for about 12 years, and these are rigid monocrystalline panels that come from Bioenno Power. You can see that they've got this nice hard aluminum frame. They've got an integrated stand in them, so you can just set the panels out, and you always want to like tilt them towards the sun so that you can track the sun with them. The connections are all on the back in a nice padded case. You can fold them up, you can transport them. These panels right here are 60-watt panels. It's the same as the power film solar ones that I have. So these are much harder to transport. So if I have to hike across LA to go get to some location I'm going to, I'm probably not going to carry these. I'll have them in my vehicle. So when I'm out in the field, I've definitely got these because they're really efficient. But I'm not going to be man-portable transporting these things here. But you can see the color on them are really kind of black. You can also see the patterns of the little cells there, where some of them have the diamonds and some of them are just wires interconnecting. Many of these solar panels, the manufacturers wire them up in a combination of series and parallel in order to get an optimal voltage and amperage out of them that's a usable size. And we're going to talk more about that in just a minute, but you can actually see that wiring here in these panels pretty well. Okay, these are the ones that I just showed. These are another type of monocrystalline panels, again, also by Bioenno. These fold up nice and small, so they can go in your backpack. These are each 28-watt panels, and then the two of them can be combined to give you roughly about 60 watts. And this is one of the ways that I set up and operate portable on a regular basis. You can just throw the panels out, and you always have your battery kind of charged up. This is the power film solar panel. Again, 60 watts on this one of power, and it's super easy. You just throw the thing out. There's grommets in the corners, so you can stake it down if you need to. You can throw it up on top of a vehicle. You can hang it up vertical on a wall. You do all kinds of things with these. They're really flexible. They're pretty expensive, but for getting power in the field and being able to carry it with you and generate your own power, these are amazing. So this is my portable power that I use a lot of times when I'm operating with my 705. So I've got my 12 amp hour BioNO battery. So it's another one of the lithium iron phosphate batteries. And you can see right there, it tells you 12 amp hours. It says, you can also see right there, it says 144 watt hours. Most of these still talk about watts that are available. Quick little aside, if you're going to fly with a battery, then there are FAA limitations on the size of the lithium battery that you can carry with you. And it turns out that maximum size that is allowed on a commercial airline is 150 watt hours. So a 12 amp hour BioNO battery or 12 amp hour lithium iron phosphate battery is the maximum size you can carry on a commercial airline with you. If you go to BioNO's site, you look in their FAQs, they have a page about this. They have something you can print out. So when I've flown with my battery, I definitely print that document out. I've got it with me. You need to take it in the cabin with you. So I carry the documentation from BioNO. I carry the specs about the battery and the information along with my ham radio license in order to be able to get through the airport security just fine and get one of these on the air. You can also see that I have my solar charge controller on there. This is the Buddy Pole Power Mini, and you can see the size that it is. It's really small, compact, and then that Power Film Solar. So this, you can pretty much stay on the air pretty much indefinitely with a setup like this, provided your battery is properly sized for your radio. Okay, so let's talk a little bit about series and parallel and the shading effects on solar panels. And to start with that, solar panels wired in series add their volts together. So if you're wiring your solar panels together in series, if you've got multiple panels, it's going to increase the number of volts that those panels are delivering out combined. Manufacturers do this. They wire their panels already so that the panels are going to put out somewhere in the neighborhood of generally under 20 volts. Usually it's around 17 volts or something like that. And that's per panel. If you wire your solar panels in parallel with each other, the amps that they produce are going to add together. And so many of the cheaper panels that you can get will oftentimes, the panels themselves, they can get away with getting the right voltage so that they work by wiring the panels entirely in, or mostly in series, so that they get that right voltage out, but you don't get as many amps out of the panels at one time. So if you were to take your own panels, you've got two sets of panels and you wire them together in series, you need to make sure that your solar charge controller can handle that voltage. Now, for emergency communication, size-wise of panels, we're generally talking about panels that are in the 28, 60, or maybe 100 watt panel size. Those are generally going to be the ones that are going to be in a size that you can physically carry with you into some location. And we're not talking about the solar arrays that you can set up for your house, or there's obviously all of those go with really expensive solar charge controllers and drive those, but we're not talking about that. We're talking about what you can carry with you for emergency communication. So keep this in mind. I wanted to touch on one other thing about this, and that is the effect of shading on solar panels. So we've got our solar panel, we've got it laid out there. Now, what happens if a little portion of that panel is shaded over? Well, if your panels are wired together in series, then you're going to get a certain amount of voltage and amps out of that panel. It's going to deliver a certain amount of current that's there. If your panels are wired together, largely the panels themselves, so each of these individual little squares, the manufacturer has wired them together largely in parallel, then you're going to get a certain amount of power out of those batteries. But what happens if you shade one little square, one of these little squares? What happens is if your panels themselves are wired largely in series, it's one of those cheaper panels, then the overall power out of your system is going to massively be reduced. the panels essentially stop functioning with just a little tiny bit of shading. Now, the first time I experienced this was back in the late 90s. I did an offshore sailing trip. I spent a month cruising the Bahamas in a little tiny sailboat, and we had to be very careful. All of our water and all of our power came from solar panels. And if like one of the lines or one of the ropes on the boat literally laid over one of the panels that we had, the way that they were all wired up, we got almost no power out. So that meant we did not have enough water to drink or enough power to run any of the other electronics that were on the boat at the time. However, if your panels, which these are oftentimes more expensive panels, are wired, the panels themselves largely in parallel, then that impact of shading on any one cell is massively reduced. And this is a really, really big deal for emergency communicators working with solar panels. So these panels that I have right here, the monocrystalline panels that I have are wired largely in series within themselves. So these panels, when they're plugged in full sun, are generating, they're 60-watt panels. They generate roughly about 4 amps of power at the right voltage, okay? When I came out to the station here at the Baker to Vegas race, at one of the times I walked out and I noticed this. See that left corner of the panel is just ever so slightly shaded. I noticed this because I walked up to the solar charge control and I read the meter, and instead of generating 4 amps of power, this thing was generating like a 1/4 amp of power. Almost no power was being generated. There's still plenty of sun here. And I thought, oh, maybe the sun's gotten too low. I need to adjust them. I moved the panels about 10 inches so that the panel was back in full sun, and bam, it jumped right back up to 4 amps of power coming out of those panels. It's a huge deal. It's something to really pay attention to when you're operating. If your panels get even slightly shaded, you may not be generating anywhere near the power that you think you're generating. So you always got to measure and keep an eye on that. By contrast, these power film solar panels, these are largely wired by the manufacturer in parallel. So you can take any one of these panels and you can cover it over, and it drops the amps that are being generated, but it's almost negligible. You can take one of these whole sides, one of the vertically, you can fold it over. So you cut the panel in half, your output then drops roughly about by half. That is incredible. You can take these panels, you can throw them out, just lay them out on the ground like this, plug them in for charging, and even if an occasional shadow goes across them, they're still going to be generating a good amount of power for you, which means you're going to keep your station on the air for a lot longer time, and it makes a big difference. So are these expensive? Absolutely. Could they be the thing that you need? Yes. These are the ones that I use most of the time now. Some of your panels can be wired together by you. Now, when you go to do this, you absolutely 100% want to make sure that your panels are compatible with each other. Generally, you only want to wire for portable MCOM use, wire solar panels together for ones that are matched by the same manufacturer, by the same power voltage, that make sure that they are compatible. So here I've got 2 28-watt panels. I can plug them together. The wiring is all integrated into these panels. You plug them together and bam, you instantly have almost 4 amps. These generate about 3.8 amps when they're combined. Of usable power to be able to do something with. You never want to take panels from one manufacturer and connect them to panels from another manufacturer. They may or they may not work, and the likelihood of them not working is extremely high, and the likelihood of them damaging your gear is extremely high as well. So don't do it. Spend the extra money to make sure you get all panels that are matched if you're going to combine them. Okay, so let's talk about an overall power system. Now, we've talked about the solar panels, we've talked about the battery. We know you've got a radio and some other gear, but the central hub, that key to make the magic of all of this stuff work, is the solar charge controller. Now, what is a solar charge controller? Let's talk about the basics of that for MCOM use. These are always required. Never, ever plug your solar panels directly into your battery. will it work? Maybe. Is it going to probably destroy your gear? Yeah, probably. And there are a lot of other problems with it. Yes, absolutely, for sure. So you always want to have a solar charge controller plugged into the panels and then use that to plug into your battery. What do these things do? They regulate the power that's generated by the solar panels, and they're managing the delivery of that power down into the radio or down into the battery at the rate that the battery is expecting. All of your different traditional batteries, your lead acid versus your AGM batteries, require different voltages and different current in order to be able to charge properly. Your lithium iron phosphate batteries require different types of power configurations in order to charge properly. And almost all of these solar charge controllers have different settings in there. You can go in, you can set them, you say, hey, I've got a lithium iron phosphate battery. You set that setting on there, and now the charge controller handles the delivery of that power correct for your battery chemistry. There's settings in all of these to be able to do that. So it's something you want to look for. They also prevent power from flowing from the battery back into the solar panels. Solar panels are not really smart devices. They take energy in from the sun, they convert it in and send it down the line, but they're just as happy to take power from your battery and radiate it out into space as heat. So almost all of these solar charge controllers have a little rectifying diode in them that only allows power flow one way from the solar panels into the battery, so you don't drain your battery and send that power back out and radiate it as heat, because that wouldn't be very helpful, would it? With solar charge controllers, you want to find a solar charge controller that is designed for ham radio. There are bazillions of these things out on the market, and 99% of the time when you hear somebody say, I'm never using solar charge controller panels because they're noisy on the HF bands and they throw all kinds of hash and all kinds of noise, that's the solar charge controller that is not properly shielded. The electronics inside are buzzy, they're noisy, and they throw out all kind of hash. A proper solar charge controller, such as the ones from Bioenno, the ones from Bioenno Power, or the ones from Buddy Pole, and there are a couple of other manufacturers, are designed to be used with amateur radio, and they are RF quiet. And that's exactly what you want. You also need to make sure that you have a solar charge controller that can handle the expected load of your radio. Now, what does that mean? Remember when we were talking about the amount of amp hours that are being drawn out on transmit? Well, when you go to draw power out of one of these, if you have the load, if you've got your radio connected onto the solar charge controller, the circuitry inside needs to be able to handle that much power. And not all solar charge controllers are created equal. For instance, the Buddy Pole one can handle 30 amps, 33 or something like that, roughly 30 amps of current draw out of them. The one that I have from Bioenno, which is a great charge controller, handles less than 20 amps out. So you got to be careful about, read the spec sheets for the solar charge controller and make sure that it can handle the load of power, the current draw that you're expecting to be able to use. You also, by that same token, you want to make sure that your panels or your charge controller can handle the expected load of power going in, the correct voltage from your solar panels. Remember that whole parallel and series thing, and you could increase the voltage? Well, if you hook your panels up, you've got multiple panels, you hook them up in series so that it increases the voltage. Well, many of the solar charge controllers that are designed for amateur radio can only handle about 40 volts coming in. And so if you wire your panels up in a different way, you can actually increase the amount of voltage to the point where you blow out your solar charge controller. Again, for MCOM use, you're carrying generally one panel with you, maybe two, and you're generally going to wire those up in parallel, so you're getting the maximum amount of amps out. So it's not really a huge deal, but it's something to be aware of. And whoops, I went backwards instead of forward. I pushed the wrong button. It's hard with so many little buttons here to be able to show that. The last thing about these solar charge controllers is there's two basic types. There's PWM and there's Mppt. Now, what the heck is that, and how do you figure out what's the right one for you? Well, let's talk about that. So we've got our PWM, that stands for pulse with modulation, and your MPPT, that's maximum power point tracking. Both of those are a big mouthful, and if I didn't have those written on the screen, I would probably flub those up all over the place. So I just wrote those up there for you. So PWM, pulse width modulation. These are generally the cheaper of the two models. They're much more economical. They work by, they've got internal switching that allows a predetermined average current to flow into the battery. And this is based on the setting that you set for what battery technology that you have. So let's say, okay, I've got a lithium iron phosphate battery. You set that in the thing in the charge controller, and then it's going to push out a certain amount of voltage and a certain amount of current out at the right amount that's going to charge that battery technology. That's what the pulse width modulation is doing. And it works by rapidly switching the power on and off. So you got the power is pretty much constant coming in from the solar panels. And all it does is turns the light on, turns the light off, turns the light on, turns the light off. And it's that right amount that's pushing into your battery in order to charge it. Now, in contrast, the MPPT, these are obviously more expensive. They're very efficient. They're little tiny computers, really. And what they're doing is they've got a controller inside that's intelligently managing the output of the solar, the power coming in from the solar panels. And it's constantly making little tiny adjustments to the voltage that's being delivered out to your batteries to maximize your charging. They're very efficient at being able to do this. These types of charge controllers are ideal for long-term operation, where the longer you need to stay on the air and the more you're trying to budget all of your power, the more an MPPT charge controller really comes into play. So that definitely raises the question then, does it really matter for MCOM use for this MPPT or PWM? And honestly, for your MCOM use, it doesn't matter. You're generally not going to be operating for days at a time, weeks at a time, months at a time, where every single millivolt is really going to count. You're trying to keep your station on the air, and the longer you start operating, more than likely the rest of the team is going to show up with other gear to help backfill whatever is needed. You're generally not going to be operating your own station for days without taking a break. So in that case, for MCOM use, it doesn't really matter that much. If you've got the money, the MPPT ones are more efficient, but you're not gonna break the bank one way or the other. Okay, so let's talk about connecting a solar charge controller to your overall solar charging system. And this really matters, the order in which you do this. You always start with the solar charge controller. You got your little box here, you're ready to go. And the first thing that you're going to do is you're going to plug your battery into the solar charge controller. And what that's going to do is going to boot up the solar charge controller. None of these things that are on the market today have internal batteries in them. They rely on drawing their power from the battery. And so you gotta have a working battery in order to boot up one of these solar charge controllers. That does present a problem. If you show up and you find out that your battery is completely dead, there are cases where you can't actually charge that sucker because you can't get your solar charge controller fully to boot up. It is a real problem, which is why a lot of us have two batteries. You got a primary and you got a backup ready to go. So you plug your battery into the solar charge controller that boots the solar charge controller. The next step, you're going to plug your solar panels into the solar charge controller. And that charge controller, as soon as it detects the power coming in from those panels, it knows what the right settings are. It begins immediately delivering that power down to the battery. And it's also checking the battery when you first plugged it in. It checks the battery and says, hey, how much voltage do you have? How much power do you have? Are you able to accept more power? If you're not able to accept more power, then when the solar panels are plugged in, it throws up a little warning on screen that says, hey, this battery is at float. I'm just going to dissipate the power from the solar panels. I'm going to push it off as heat and not burn up the battery. It really is managing the whole charging process. Finally, you're going to take and you're going to plug your load or your radio, in this case, into either the load ports on your solar charge controller Or if your solar charge controller doesn't have the capacity to handle the expected load, you would connect your radio directly to the second port on your battery. Notice how most of these batteries have 2 ports on them. This is the standard power pole connection we're all used to. This is the 50 amp power pole connection, and you can either clip the leads off and just put the one on that's going to be more appropriate for you, or you can just make a little power pole adapter and adapt the 50 amps to the regular 30 amp power pole connectors. Okay. So that's the order. Battery first, into the solar charge controller, then your solar panels, then your radio. Okay, this is the solar charge controller that I have. That's from Bioenno. Here you can see I had to wire in my own little connectors for it, and I color coded them. So the yellow terminal there, the sun is yellow, so I put a little bit of yellow heat shrink on it, so I know, hey, stupid, plug your solar panels into the yellow port. The green one, because I'm using the Bioenno batteries, there you can see, look, I've got a green screen behind me, and the battery disappears. They're green, so I know I plug my battery into that port, and then white is the load. That's the power going out. This solar charge controller can only can handle less than 20 amps of current draw from its load port. So when I'm running this one, I plug the load directly into the battery. There are also USB ports on there, so you can plug a USB device directly in. That's perfectly acceptable to be able to do. And you can charge your cell phone or what have you directly from the solar charge controller. You can see there's a little LED screen up there so that you can do the controls and make the settings, monitor the power that's going in and out of the battery. This one's the Buddy Pole Power Mini. This is the one that I use now pretty much all the time. And these have the nice display. It tells you the system voltages for both the battery and the solar panels that's coming in. It tells you the amps that are going out and in on the appropriate side. And it also tells you the net amp hours that are coming out of the battery and that are going into the battery. This is that budget that you've got. All the devices you have all tell you how many amps of power they draw. You just add those all up together and it tells you what your current draw is. That's how you get that nice amp hour connection. So while we're looking at this, let's do a quick little review here because this really is so important. The first thing when we're going to boot this sucker up is we're going to plug the battery into our solar charge controller. The second thing we're going to plug in is going to be the solar panels. And you can see over here behind me, you see that little bit of yellow here. That's the yellow tag that I've got on my solar charge controller or my wire. So I always know, hey, this one goes into the sun port, the red one, the yellow one. And then finally you plug your load in. The Power Mini has 2 load ports that you can plug 2 different devices in. And there's also a USB port that's here on this side that's connected. So you can plug a USB device directly into here as well. So that's the Power Mini. Now I've just got a couple of pictures of a few of the solar setups that I've used previously. This has the 60 amp hour rigid panels that I've got. You can see on the back side of that is where the battery is. And the solar charge controller is hidden under the shade. A lot of these panels are nice because they've got the little stand. You never want to leave your batteries or your charge controller out in full sun. And so you can a lot of times just tuck them underneath of your solar panels in that little bit of shade that's provided right there to keep the battery cool and to keep your electronics cool. In this case, I've got my power inverter connected up and I'm running my laptop, and the pole that's going up there behind there has a mesh node on it. This was at field day in 2019, and we were making a connection from the Nike site across to Verdugo, a 23-kilometer shot across the San Fernando Valley, and we had a full connection onto the Arden mesh network. So this particular setup here is running a mesh system that's ready to go there for emergency communication use. This is winter field day 2019. I've got my Mastworks and my Buddy Pole connected there. You can see my panels that are set out, and we ran the station all day long, no problem, keeping the station on the air while we operated with backup from solar into our emergency power. Here's one of the operations. I a lot of times we go up to the backside of Mount Wilson and set up and operate. And underneath of the panels that are here on the ground, I've got the solar charge controller and a backup battery. That's all up there on charge. And then up on the picnic table, you can see I've got my other panels that are while I'm actively using. So that's keeping that battery up on float. You can pretty much operate like this pretty much indefinitely at that point. This is another field day 2019. You can see a different set of panels. These are also monocrystalline. You can see the characteristics. They're black panels, and they also have the little diamonds in them, which is another kind of indicator. It's not a dead giveaway, but it's one thing that you can kind of look for. So these are also, and you can see you can just hang them up and they're going to generate power. Now, the better you can angle your panels to the sun so that they're always pointed at the sun, the more power that they're going to generate. So these are doing pretty good. They're not doing as well as they could be, but it just shows that you can just throw these things up and then you're going to basically trickle charge in the background your battery. Here's another setup I do. This is at the marina that I was living at. I would oftentimes just go up and I would set my antenna up. I would throw the solar panels out. I've got my solar charge controller. There it is. I point this way. I got the solar charge controller, the battery. Here I've also got my iPad that I'm using for logging, and the iPad is connected into the USB port of the solar charge controller, and the radio is connected onto the load port. So it's completely self-contained to sit there and operate a little Bluetooth keyboard, and you're good to go. You're ready to go with that. So that brings us back to Baker to Vegas, which is where we first started talking about this. This is actually the night before the race started, and I was just topping up the battery here. I've got the panels laid out. You can see how the arrangement where the battery and the charge controller are just tucked in under the shade because out there in the desert, it does get really hot, and heat can damage all of your electronic equipment. So keeping it in the shade works. Top these things up and we were ready to go. So during the race, that's exactly what we did. We used the battery to create the immediate power for the radio to keep the MRK and get that up on the air. And then we backed that radio up, the battery up, with the solar panels that were constantly trickle charging throughout the entire day, keeping that battery pretty much at float all day long. I keep mentioning this word float. That means that the battery charge level is floating right there at the full charge level. And it's perfectly acceptable to be able to do that with this battery technology. Not all battery technology likes to be kept at a float charge. You need to check with your manufacturer's information to find that out, what's right for there. And that brings us to this slide that we looked at earlier. And this is a little bit of interesting information because this is actually the next day after the race. We kept the radio on the air the full 15 hours. And this is the next morning. When I went back to my room, I plugged the charger for the wall charger into the source on this side. And I plugged the BioNO battery into the load. And so the values that you see is how much power we ended up using out of the battery over using the radio, using this battery, a 30 amp hour battery, to keep that MRK radio on the air for 15 hours. And it ended up being only 5.206 amp hours is all that battery took to come back to a full charge after keeping that station up and operating, even with that really high current draw all day while it was being used. And that's because the solar panels were able to keep that battery at float, which meant we could have kept operating for a considerable amount more time before we would have needed to switch that battery out had we needed to keep the station on the air in the middle of the night. So there we go. With that, I just say thank you, and happy to take any questions that folks may have.